All right, let's get right into it. In the world of Formula Student Electric, winning isn't just about who has the most power anymore. It's all about strategy. Today, we're cracking open the playbook of a senior consultant to show you the disciplined, data-driven thinking that separates the teams on the podium from everyone else. This is the real blueprint for building a world-class electric race car from scratch.
So picture this. You've got a brilliant team, you've got real ambition, and your workshop is full of carbon fiber and high-voltage parts. You're all set to build a winner, right? But what's the one thing, the single hurdle that trips up almost every single new team? I'll bet it's not what you think.
More than 40%. Just let that number sink in for a second. That's how many electric teams failed to finish the single most important event of the whole competition, the endurance race. They get a DNF. Did not finish. After an entire year of blood, sweat, and tears, 40% of teams score a big fat 0 on the one event that matters most. So why? Well, it's because they fall into the classic rookie trap. They get obsessed with peak horsepower, with blistering one-lap speed. But the professional teams, they know the secret isn't just about being fast. It's about being fast for 22 kilometers straight. They build for reliability because they know that is the only way you're ever going to win. So how do you avoid that trap? Simple. You adopt a professional strategic framework. When you really analyze the rules and the winning teams, the entire challenge boils down to 3 critical value levers. If you can master these, you've got the most direct path to the podium. And here they are, the 3 pillars of a modern winning strategy. First, you have to prioritize reliability, just to make sure you actually finish the race. Second, you use software to unlock performance that the hardware alone could never deliver. And third, you design the entire system for maximum efficiency. Because in this competition, speed and saving energy are really just 2 sides of the same coin. And look, if you don't believe me, just look at the math. This chart proves the point. The endurance and efficiency events together are worth 325 points. That's nearly a third of the entire competition. If you get a DNF here, it is mathematically impossible to win. It's that simple. This is exactly why reliability has to be lever number 1.
Okay, let's dig into our first lever. And this is about so much more than just using strong bolts. It's about surviving what consultants call the valley of death in product development.
The valley of death is that treacherous gap between having a collection of individually brilliant parts, a powerful motor, a high-tech battery, and having a fully integrated system where everything works together perfectly. This gap is where most projects fail. It's the difference between a cool science project and an actual race car. So what are the specific disasters lurking in that valley? Well, it's things like the motor overheating because your cooling model wasn't quite right. It's the battery voltage sagging under load and triggering a system shutdown. It's a tiny software bug in the control logic, or even something as simple as electromagnetic noise from the power cables scrambling your sensor data. These are the fatal system integration failures that knock 40% of the field right out of the race. Okay, so once you've built a car that can actually survive, how do you make it fast? Well, the rules cap your total power at 80 kilowatts. So the new frontier, for performance, it's not in raw power anymore. It's in code. Let me explain. Top teams are using advanced algorithms, like torque vectoring, to precisely control the power going to each individual wheel. This helps the car rotate through corners way better, effectively creating grip and speed beyond what the physical tires can handle. It's pure performance, literally written in software. But, and this is a big but, testing this kind of complex software comes with a massive risk. The single most inefficient and frankly dangerous thing you can do is debug your control code for the very first time on the finished car. One little bug could destroy an expensive inverter, or even worse, create a really serious safety issue. This is where the professionals use a technique called hardware in the loop, or HIL. The best way to think about it is like a flight simulator for your car's electronic brain. You take the real vehicle control unit and plug it into a powerful computer that simulates the entire car and the racetrack. This lets you safely test every possible scenario, from a sensor failure to a full 22-kilometer race, all from the comfort of your lab. IL is a critical step in a very structured process, a kind of verification pyramid. See, professionals de-risk their software in stages. First, you have model in the loop, or MIL, where you just test the pure algorithm in a simulation. Next up is software in the loop, SIL, where you test the actual compiled code on a PC. Only after that do you move to hardware in the loop, testing the code on the real controller. By clearing these gates one by one, you systematically kill the risks before you ever even touch the physical car. You make sure the software is bulletproof. Now, the absolute pinnacle of this software-first approach is something called Model Predictive Control, or MPC. It's basically like having a digital co-pilot that's constantly predicting the car's behavior and making optimal adjustments. And as this table shows, the driver can literally tune the car's handling with a keyboard, not a wrench. If the car understeers, you tweak a software weight to make it more agile. If it's a bit unstable, you tune another parameter to smooth it out. This is what we mean by software-defined performance. Okay, so with a reliable car and some really intelligent software, we can finally tackle our third lever, efficiency. And there is no greater test of all three levers working together than the final boss of this competition, the 22-kilometer endurance race. This is where every single engineering decision you've made gets put on the line.
22 kilometers. You know, it might not sound like much, but on a tight, winding track, going at race pace, it is an absolute eternity for an electric powertrain. This distance is the great filter. It's designed to break any car that has even the slightest weakness in its design. And the number one reason cars break? It's heat. When you're continuously drawing high current, the battery and motors generate a ton of heat. And if your cooling system can't get rid of it fast enough, temperatures skyrocket, parts start to degrade, performance just tanks, and, well, your race is over.
Success in the endurance race really comes down to this incredible balancing act. You have to manage your limited energy budget and control your thermal limits, all while trying to go as fast as possible. If you push too hard on speed, you'll overheat or you'll run out of battery before the finish line. It is an incredibly difficult optimization problem to solve.
This brings us to the final, and honestly, the most important lesson in the entire playbook. For any new team, your entire strategy has to be built around one single core idea.
Your goal is not to set the fastest single lap time in practice. Your goal is to cross the finish line after 22 kilometers. You have to redefine success. It's not about peak performance. It's about sustained, reliable, and efficient performance. Because for a new team, the first real victory, it isn't lifting a trophy. It's that handshake you get from the official who confirms you finished the endurance event. That's what proves your engineering process works. That is the foundation you can build on to go chase trophies in the years to come. So the question is, what will you build your foundation on? Brute force or smart strategy?